So we're going to look at Maxwell's equations and see how we can derive light as traveling waves based on those equations. So let's start by writing down the 4 equations. Firstly, we have Gauss's law, which says that the flux of the electric field through a closed surface is the charge inside divided by epsilon naught. So that's Gauss's law, and that's essentially telling us that electric field lines come out of positive charges and go into negative charges. And then alongside that, we have the same thing for magnetic fields, the flux of a magnetic field through a closed surface, and that's always 0, which is to say that there's no such thing as a magnetic monopole. Electric field lines always form closed loops. And then we have Faraday's law, which is a path integral of the electric field dot dl around a closed path, and that's equal to minus the rate of change of magnetic flux through that path. So that's Faraday's law, and that tells us that if you have a changing magnetic flux, you're going to generate an electric field that goes in loops. And finally, we have the path integral around a closed path of the magnetic field, B dot dl, and that has 2 terms. The first one is Ampere's law, mu naught times the enclosed current, and that tells us that if you have a current, you'll generate a magnetic field in circles around it. But there's a second term which Maxwell himself added, which is mu naught epsilon naught d phi E dt. And that tells us that if you have a changing electric flux, such as when you're charging up a capacitor, you're going to generate a magnetic field in loops around it. So these are the 4 equations that Maxwell wrote down, and you add to that the Lorentz force law, F equals QE plus QV cross B, and that tells us the force on any charged particle that might be present. So that's where we are now, and our job now is to try to find solutions of Maxwell's equations in a vacuum. That is to say, we're far from any charges and currents, somewhere out in space. So there are charges and currents elsewhere in the universe, but they're not here. And if that's the case, then we can immediately cross out the enclosed charge, because there is none, and so that's going to be 0. And similarly, the enclosed current is going to be 0. So now we have Maxwell's equations in a vacuum, which take on a simpler form. And what Maxwell showed was that these 4 equations here have a solution that's a traveling wave. And that's what we're going to look at now. So what do we mean by solution? We mean that we have a pattern of electric and magnetic fields somewhere in space, away from any charges and currents, where all 4 of these are satisfied. So there are many such solutions, in fact, infinitely many. And these equations are linear. So if I find a couple of solutions, I can combine them in a linear combination, and I'll have more solutions. So I'm going to draw now a simple solution of these equations, and that's a slab of fields. So think of a thin vertical slab that has a vertical electric field pointing like this. And then there is a magnetic field that is coming towards us out of the page, like that. And those 2 things are perpendicular to each other. So there's the magnetic field. And this is a thin slab, so the fields are confined to this region. It's very tall in all directions, but it's very narrow. So I'm going to show you now an example that I've just made. So here I've drawn my electric and magnetic fields on this box, so you can see the slab as I turn it sideways. So in this narrow slab, you have to imagine it extends in this direction infinitely far. Now, this in itself is not a solution of Maxwell's equations, but it can be a solution if it's moving. So we have to get this pattern of fields moving to the right with exactly the right speed. What happens then is in front of the slab, we get an increasing flux of electric and magnetic fields. And if you put them in Maxwell's equations, you'll find that it works out just right, provided the speed is exactly right, as we're about to do. Now, if you want to remember which way round they go, it's quite easy. You use the cross product rule. And the cross product of E and B, using the right-hand rule, points in the direction that the slab has to move. So this slab is moving to the right with speed v. And what we're going to do now is apply Maxwell's equations to this slab and show that it's a solution. Now, the first 2 are true. There is no flux around any imaginary closed surface that I draw here, because all of these field lines extend to infinity. So the first 2 equations, Gauss's law, are automatically satisfied. So it's the second 2 equations that we have to care about. So we're going to apply them one at a time. The first one we're going to apply is Faraday's law. Now, in order to do that, we're going to draw this with a view from the front. So if I draw my slab of fields like this from the front, then the electric field is vertical, like this, So this is the view from the front. And the magnetic field is coming towards us. So I draw some red dots like this. And remember, this is extending vertically in a very vertically in a long direction, but it's only very narrow. And this pattern is moving to the right with speed v. Now what I'm going to do is I'm going to draw an imaginary loop and calculate the path integral around that loop. And my loop is going to be a rectangle that is partly inside and partly outside the region of field. So the vertical height of my loop I'll call L. And I'm going to label this little distance in here as x. So x is the distance that my path extends into the field. Now, as the field pattern moves to the right, x is going to change. Now, I have to decide which way round to go around my path, and I'm choosing to go around clockwise. That's up to me, that choice. But after that, everything else is fixed. Okay, so now I have to do the calculation. So on the left-hand side, I have the integral around the closed path of E dot dl. So that's going to be equal to the strength of the electric field along this line here multiplied by its length. So that's E times L. As I go along the vertical side here, I've got a length L and an E. The other sides all give 0. The electric field is 0 in this region, and in this region it's perpendicular to the path. So that's it. That is the left-hand side. The right-hand side is minus d dt of the magnetic flux. So the magnetic flux through that path is the strength of the magnetic field, B, times the area that's enclosed. Now the area is the length times x, because that's the bit that's inside the field. So the flux is in this region here. Now I need a minus sign here. The reason I need a minus sign is because according to the right-hand rule, I'm going around this path in that direction, and so a positive flux will be pointing towards me, but this one's actually pointing the other way. So that's why that minus sign's in there. The two minus signs cancel, and I'm left with B times L times V. Where did the V come from? That's just the x dt, so the rate of change of x. Okay, so that's the view from the front. If I equate those two, left-hand side and right-hand side, I get the simple equation that E is equal to B times V. In other words, this pattern is able to satisfy Faraday's law, provided this condition exists. That is to say that the electric and magnetic field magnitudes have to be in this particular ratio, where V is the speed. Okay, now we're going to draw the view from the top, from above. So from above, I see electric field lines coming towards me. Whoop, electric field lines are in blue. And I see magnetic field lines that are heading downwards, like this. So there are the magnetic field lines. And I'm again going to draw a rectangle. And my rectangle will extend again, partially in and partially out, like so. And it has, again, the same length and the same x here. X is the distance that it goes inside. And this time I'm going to transverse anti-clockwise around it, like so. And then I do the integral. So the left-hand side of my integral is the left-hand side of this equation here. So it's the integral of B around the loop. And again, it's only on this left-hand side here that we see anything at all. It's the magnetic field multiplied by the length. So that's just equal to B times L. The other sides contribute 0. The right-hand side of this equation is mu naught times epsilon naught times d phi E dt, like so. So mu naught, epsilon naught, of course, are constants of nature. And the flux of the electric field through that path is the strength of the electric field times the area, which is again the length and the width of the rectangle. Now this time I don't need any minus sign, because the way I've drawn the loop, as I go around the loop using the right-hand rule, the flux is positive. So this is mu naught epsilon naught E L V, because the derivative with respect to time of x is v. The other two are constant in time. So equating left-hand side to right-hand side, I get B equals mu naught epsilon naught EV. So that's telling me that the magnetic field and the electric field are in this ratio. So now I have two equations here, and all I have to do is substitute the second equation into the first equation, and I'll be able to derive an equation for the speed. So I'll let you do this yourself. It's only a couple of lines of algebra, and what you will find is that V has to be 1 over the square root of mu naught times epsilon naught. So that's only a couple of lines. And this is what Maxwell himself did. At this point, I'd love you to pause the video, take out your calculators, and plug in the values for mu naught and epsilon naught that are known experimentally. These were known to Maxwell himself to a few percent. So do that right now. Okay, so if you put the numbers in correctly, you should find that this is equal to 3.0 times 10 to the 8 meters per second, which of course is the speed of light. And Maxwell himself did that calculation and he got that number. And at that point he got extremely excited. He was Scottish, so I won't try to do the accent, but he basically said, at this point we can scarcely escape the conclusion that light is a traveling pattern of electric and magnetic fields. And that's exactly what we've shown with this. So now we have it. We have our solution of Maxwell's equations, which is this slab of fields moving across to the right. Now you might be wondering what creates this slab in the first place. And the answer is accelerating charges. So somewhere way over here, there are some charges that have been accelerating, and they have produced a pattern of fields that's propagating outwards at the speed of light. Now they've reached us, they're moving across this way. So real light actually comes from oscillating charges. They're accelerating more or less in simple harmonic motion. And we see a pattern like this. And you can see that there's a wave with a particular wavelength and frequency that's propagating to the right, with electric and magnetic fields always perpendicular, always traveling in the direction of E cross B, like this. Now another thing we can do with this experiment is imagine, as Einstein did, what happens if you travel along with the light. So if you imagine in my frame of reference, if I move along with this pattern of fields as it's moving, and I try to analyze it with Maxwell's equations, I'm not going to get a solution. I'm going to find that this pattern violates Maxwell's equations, because according to me, it's stationary. And in fact, from what we've just done, the only possible speed that this pattern can have is c, 1 over square root mu naught epsilon naught. No other speed is allowed. And Einstein took the extraordinary step of saying he trusted Maxwell's equations, and he said that for any observer, no matter what they were doing, they would always see light moving at exactly that speed. And that's, of course, the postulate that led him to the special theory of relativity in 1905.